Hello and welcome to this Reigate College Further Maths video on linear transformations. You'll have met linear transformations before, general transformations at GCSE, when you've looked at reflections, rotations, translations, and you've also met transformations of graphs in your pure maths studies. Turns out that transformations can be represented using a matrix, so that's where it comes into the work we're currently studying. So if you've got a transformation T, you can multiply a point by a matrix and it maps it onto a linear combination of the x and y coordinates. So if we've got 2x plus 3y and x plus 4y, we can represent that using this matrix here, 2, 3, 1, 4, and you can see that if you multiplied that out, you'd get 2x plus 3y and you'd get x plus 4y. This particular matrix doesn't represent a transformation that you know. That's not a rotation or a reflection, but we will come on to how we work out what the transformation is. A couple of things about transformations that are important. The origin is always an invariant point, because if you think of a matrix, multiplying it by the point 0, 0, if you had here, then that's always going to map onto the origin. And also this, if you've got a multiple of a vector and you apply the transformation to it, it's the same as doing the transformation and then multiplying by something. And also that if you combine 2 points together and transform them, it's the same as transforming them separately and adding them. This is something that you might study a little bit more if you go on to university and look at vector spaces then. We've got a couple of important things to consider. Do we have any invariant points? Are there any points that stay exactly where they are? So for example, if we've got 1, 1, when we transform it, when we reflect things in the line y equals 1, that point will stay where it is. And also an invariant line is a line that's mapped onto itself. The individual lines, points might change, but the line will be invariant. So if you think of a reflection in the y-axis, the line y equals 6. So if we think of, here are our axes, if we reflect in the y-axis here, then the line y equals 6, which goes along here, that will be reflected. So it will still be the same line, but individual points will change where they are on that line. So let's have a look at some transformations and check whether or not they are linear. So here we have mapped, this is a mapping, and it's mapped the point x onto x plus 3 and y just onto y. Now this is not a linear transformation. This is not linear. This is actually moving things 3 across to the right. The reason that we can tell that it's not linear is that if we were to look at, for instance, what happens to the point 2xy, sorry, 2x, 2y, so if we multiply that point by 2 and apply t to it, we would get, so this says map it onto x plus 3, so that would be 2x plus 3, and then the y just maps onto itself. Well, that's not the same as 2 times this result here. So that's not equal to 2 times t of xy. So that's not linear. This one is a linear transformation. We've got a linear combination. So we must have x's and y's in the mapping here. That's how we tell that one isn't linear. So this is linear. And the matrix for it is 2, 3, 1, minus 4. You just use the coefficients of the x's and the y's. This one here is not linear. And the reason for that is this x squared. If you think about this one, if you looked at the point 3, 0, no, 3, 1, what's t of 3, 1? going to be? Well, that would be 9, 3. But suppose we look at t of 2 times that vector, so that's 6, 2. Well, that is going to be 36, and x times y, 12. That is not equal to, so t of 2 times the vector, 2 times the vector 3, 1, is not equal to 2 times t of 3, 1. So this doesn't come in very much into the studies we do, but it is important that you know that that's what the definition of a linear transformation is. So let's have a look at how we actually go about using the matrices for these. So we're looking here at transforming a point P. So the image is P dash, and it's given by multiplying the point by the matrix. So the matrix can be found by drawing a sketch and considering the images of the unit vector. So we'll see how that happens in a moment. If we want to actually generate the new points, the way you would do it is here's the matrix. Suppose I want to know where a point given here. Suppose I want to know where 3, 4 ends up under this matrix. I would multiply it like that. So I would get 6 and 12 is 18, and 3 and 16 is 19. So that's where this point would map to under this mapping. But what the matrix is telling you is the columns tell you when 1, 0 is mapped to, the first column, and the second column tells you where 0, 1 is mapped to. And that means if we've got the matrix, we can get the transformation. If we've got the transformation, we can get the matrix. There are some standard transformations, and some of these are given in the formula book. So you've got reflection and a line through the origin, and we've got rotation about the origin, and we've got then these different transformations here, enlargement and a stretch parallel to the x-axis. So we'll see how these come out in a moment. So the way we work through these is, if you want to find the matrix representing a transformation, you consider what happens to 1, 0 and what happens to 0, 1. So here's 1, 0. And I tend to do this in 2 different colours. Hopefully the colour will come out on the video. So we've got black and red here. And I draw 2 sets of axes. The first one for the original position, the second one for where they end up after the transformation. So an enlargement scale factor 3. Well, the vector 1, 0 is going to end up at 3, 0. So that means the first column of the vector is 3, 0. The vector 0, 1 is going to end up at 0, 3. So that means the second column is 0, 3. And that's the matrix. For B, reflection in the line y equals x. So I'm going to draw in my starting vectors. I'm going to draw in a dotted line, the line of reflection. And I'm going to think what happens to these 2 vectors. So I'm reflecting it in the line y equals x. So my black vector is going to end up here. So this is the black vector. I'm not sure the colour is coming out well on the video, so I'm going to draw it slightly thicker for the black one. So where does 1, 0 end up? It ends up at 0, 1. Where does the red vector end up? Well, in this reflection, it's going to end up at 1, 0. So they swap over. So this column here of the matrix is going to be 1, 0. So that's a reflection in the line y equals x. Part C, we're looking at the stretch parallel to the x-axis, scale factor 2. So I've got my unit vectors here, and I'm going to see where they end up. So I'm going to stretch it parallel to the x-axis, so this direction, scale factor 2. So this vector here is going to end up twice as big, so 1, 0 is going to be mapped to 2, 0. So going to stretch it in that direction. But what's going to happen to 0, 1? Well, 0, 1, if it's stretched in this direction, it's just going to stay where it is. So that's going to stay at 0, 1. So that is a stretch in the x direction. Now the last one here is a rotation. So we've got my 1, 0 vector here, and I've got 0, 1 there. Now I'm rotating it 45 degrees, so it's going to rotate to there, and it's going to rotate to here. Now, it is important that you can think about what's going on here. This angle here is theta. So just by some fairly straightforward trigonometry, this is 1, this unit vector. So the across bit, the x coordinate of the new vector, is cos 45. And the vertical component there is sine 45. So that's the first column. Then we think, where does the red vector end up? So the red vector ends up here. Now that's going to be minus sine 45 and cos 45. Now this matrix is given for an anti-clockwise rotation of theta degrees about the origin. That is given in the formula book, but you should be able to follow where it comes from. So the last section that we need to look at is finding the transformation. So if you can be given the transformation and you need to find the matrix, or you can be given the matrix and you need to find the transformation. So we follow the same process for each of these. Think about, where do the unit vectors end up? So if we start with this one, we've got our unit vectors looking like that. Now, where do they map to? We can see that 1, 0 maps to 2, 0. You don't need to multiply it out. You can just read it from the matrix. So that maps to 2, 0. And the red one, the j vector, if you like, maps to 0, 2. So you should be able to see that this is an enlargement, scale factor 2, about the origin. Now, what points are invariant and what lines are invariant? So the origin definitely stays where it is. So invariant points are 0, 0. Invariant lines, what lines stay the same? Well, if you think of enlarging this, in this example, any lines through the origin will be invariant. They will just be mapped onto themselves. So invariant lines, any lines through the origin. Other lines will not be invariant. So if you imagine a line like x plus y equals 1 here, if you stretch that, that's going to move to a different line, x plus y equals 2. So let's have a look at the next one. So that was A. So for B, we've got 0, we've got the I vector and we've got the j vector. Where do those map to? So 0, 1 maps to, let's look at here, 0, minus 1. So that maps down to none across minus 1 down there. You need to be quite deliberate about where things are going and watch that you're plotting the right points. And then the red vector ends up at minus 1, 0. So that goes like that. So what's happened here? This is a reflection in this line here. So this is a reflection in the line y equals minus x. Now, what points are invariant? So invariant points, 0, 0 is invariant. Anything else invariant? Well, anything on the mirror line will be invariant. So all points on the line y equals minus x. But there's another invariant line, because the line y equals x, which goes here, that will be invariant because it will fold over onto itself. And in fact, any lines that are perpendicular to the mirror line will map onto themselves. You wouldn't be asked in an exam question something as vague as this. They will be more specific than that, but it's just good to think about which lines are staying the same. Right, part C. With this one, you should really recognise, and once you've done a few questions you will, that this is going to be something to do with angles, because these are all exact surds, that sort of thing. So this is going to be a rotation. And what I would advise you do in this case is to use the general formula given in the formula book, that the matrix for rotation looks like this. So we've got cos theta sine theta minus sine theta cos theta, and then match that up with the matrix that you've been given. So we can see that cos theta is √3/2. And we can also see that sine theta is 1/2. You do need to just check both of these to work out what the rotation is, what the angle is. So theta is 30 degrees. So this is a rotation anti-clockwise, 30 degrees, about 0, 0. 0, 0 is an invariant point, but there are no invariant lines. If you think of any line, it wouldn't be mapped onto itself in a rotation. So you can either use this method, or you can sometimes compare with what's in the formula book to try and work things out. But you need to be able to go from a description of a transformation to the matrix, and you need to be able to go back the other way from a matrix to the description.